Now, last night's celebration was instructive for both the beauty and the pageantry and the passion for this university, but it also provided me an opportunity to talk a little bit about what I'm going to talk about today. The title of the talk, The End of Moore's Law. And Moore's Law is something that I would like to introduce it, actually, with a little bit of things here. In my pocket, I took from the hotel. These are called matches. And if you do this, it goes on. I don't know how many of you have ever been in Verona, which is a city in Italy. And in the center of the city, they have this amphitheater, and they perform in the evening during the summer operas. And before the opera starts, as it gets dark, everyone in the audience takes out a match and lights the match, and you see the beautiful light from all these matches throughout the amphitheater. And people have been doing that for centuries. Now, last night, during the celebration, at one point during the evening, we were asked to take out something that they gave us, and we produced light. We didn't have matches, which is a technology that comes from the time of what they say Prometheus, thousands of years ago. We have a computer here connected, and we get light. So things have changed over the years, things we take for granted. Also last night, they gave us this. And they said that if you Now, you don't need a very fancy computer to make this happen. A very simple, boring computer from maybe 50, 60 years ago would be good enough to do this. I need to make it work. No, there it is, out. But they also had last night, in addition to this, which takes a very slow, boring computer from the beginning of computers. First computer, by the way, on a single chip was in 1971, a microprocessor introduced by Intel Corporation. It only had 2,300 transistors, and it ran at a very slow frequency comparatively, 100 kilohertz. But they also had last night, I don't know how many of you saw the presentation. It was web broadcast, and I understand it's available so you can see it at your convenience. But one of the things that was spectacular about that performance last night was the use of computer technology to show incredible graphics. The computer that is powering this would not have been good enough to do the graphics that we saw last night. Now, what's my point? That we take it for granted that every year we're going to see more and more capability, and we're going to be able to do more and more things than we could do before. It's based on Moore's Law. Moore's Law is a very simple observation that an American engineer named Gordon Moore made back in 1965. He noticed, as he did his calculations, that the number of transistors, those simple little things that actually make the decision structures that go into the computer, that the number of these things on a single chip is going to increase. That number is going to increase. That number is going to double every year. And then 10 years later, he redid the analysis and said it's going to double every 2 years. For the last several years, it's been doubling a little bit more slowly, but nonetheless, it keeps doubling. It's known as Moore's Law. So in 1971, there were 2,300 transistors, and they ran at 100 kilohertz. Today, there are 10 billion transistors. 2,300 to 10 billion. 2.3 thousand to 10 billion. 3 orders of magnitude. And instead of 100 kilohertz, they're running at 4 gigahertz. 100 kilohertz to 4 gigahertz. Again, almost 3 orders of magnitude. Now, with all those transistors, 2 things happen. First of all, in order to make the doubling happen, we need to make the transistors smaller. And with smaller transistors, we can have so many more of them on the chip that it provides opportunity for people like me to invent structures that allow processing to happen faster. So that instead of the computer that can do this, we have the computer that did that incredible graphics last night in the auditorium. It's also the case that as the transistor becomes smaller, it can switch from conducting to not conducting much faster, which is what allows the frequency to go from being able to do 100,000 steps in each second to being able to do 5 billion steps in each second. So going much faster allows us to do things more quickly, and having more transistors allows us to do more things that are interesting. And the result is what you saw last night in graphics. Or if I back up 40 years ago, it's the light switch rather than the match. The problem is that as these transistors are getting smaller and smaller, we are finally getting to the point where we can't make them any smaller. And so we say Moore's Law, which has allowed us to continue to get more and more, faster and faster, is coming to an end. Now what's that going to mean? So my title, An Obstacle to Discourage, that is to say, Moore's Law is over. We're not going to get more transistors. We're not going to get them faster. Or is it an opportunity to embrace? Can we use what we've got in more interesting ways? And we can, providing we do certain things. We'll get to that before we finish today. So what I want to do today is several things. First of all, talk about Moore's Law, which I have already started to do. Then I want to mention the von Neumann paradigm, which is the way computers have been executing for the last 50 years. Actually, more than that now, 70 years actually. And some people say that that too is over. And I want to tell you that no, it's not over. The von Neumann paradigm, which I will explain, will be with us for a long time to come. And then I want to tell you about the transformation hierarchy, which is necessary if we're going to continue to get the benefits like we had, like going from this to those graphics that we saw last night. And I've picked a few cases. I could have picked 10, 20, 30 cases, but then we would have had to send out to bring us breakfast because it would be tomorrow morning before we would finish. So I picked 3. And then what I want to do is say, okay, now that we have the situation, the landscape, what do we need to do moving forward so all those dreamers who come up with new and better uses for computers will have the ability to make them faster and do more things. So first of all, Moore's Law. I've told you what it is. It's a doubling of the number of transistors on the chip. Every time I do a new, what we call process generation, which is a new chip technology, which today is every 2 or 3 years, we double the number of transistors. But we're now getting to the point where these transistors are very small. The technology that we're working on is, we call it 7 nanometers. A nanometer is 10 to the minus 9 meters. But most of us, we're not comfortable with the term nanometer because we just don't visualize nanometer. But if I tell you that 1 nanometer is 10 angstroms, and you studied angstroms when you took chemistry in class, then the 7 nanometers is 70 angstroms. And angstroms is what we use to measure the size of molecules. So we're getting real tiny. And Moore's law will end because we can only get so tiny. When we get to the point where we are operating at a fraction of an electron, we're in deep trouble. So Moore's law will end. We can't get any smaller. What I put on the slide is it a law of physics, microarchitecture, psychology? The truth of the matter is it's actually a law of psychology. Many people said many years ago that we could never get the transistor any smaller. And if we got it no smaller, we wouldn't be able to keep doubling. But we continue to get it smaller. How do we continue to get it smaller when everybody says we can't get it any smaller? The answer is pretty simple. We have in my country, in Silicon Valley, in California, a company. And the applied physicists, the technology people, are working at making the transistor smaller. And they say to the boss, we are done. We can't make it any smaller. And the boss says, make it smaller. We can't. Make it smaller. If you don't make it smaller, and that company over there makes it smaller, you will end up not being a process technology person, but you'll be selling chicken at KFC. So you better make it smaller. While that's happening, another company, make it smaller. We can't make it smaller. If you don't make it smaller, and they do, you'll be selling chicken at KFC. And so what has happened over the years is because they've been told they must do it, they've continued to be able to make it smaller. In fact, it used to be, years ago, that the transistor on the chip used to lie flat. Then somebody noticed, in fact, you people have noticed this when you build the dormitories on the campus. Is the dormitory 1 floor up and covers all this space? Or is it not very wide, but it goes this way? And so what has happened with the invention of the FinFET, the transistor no longer goes this way, it goes this way, takes up less area, so it can continue to double. But that's only a very short-term solution. The psychology has caused the doubling for a long time, but we are essentially done, and everybody agrees that this time it's really going to happen. Moore's law will end. We will not be able to go any faster, and we will not have any more transistors on the chip. And so what does that mean? That people in other fields, like the graphics that we saw last night, will not be able to produce fancier and fancier graphics? That the movies that you watch with all that, what almost looks like magic of how incredible the visual displays are, will not be able to improve? Or can we do something with the existing technology, do it better? So that's the question. Is it a time to give up, or is it a time to see if we can do better? So what do I say? What Moore's law did, by doubling the number of transistors on a chip, it enabled smaller transistors, which gave us more performance, more transistors, which gave us more functions that people like me were able to invent to make this happen. Why it cannot go on forever, I've already told you. Another good thing that's happened is that these more and more transistors that Moore's Law has allowed has created new needs and new problems. They've given way to newer paradigms that enabled us to be able to do more and more new things. I said earlier, the dreamers, the people that say, oh, if I only could do such and such, I could accomplish a lot more. And we're going to see that. We're going to see the day where every person has a little microprocessor in their body controlling their health care. Because even though we think of humanity as a collection of people, we're all individuals, and we all have different allergies, and we all have different immunities and different tendencies, and a computer on each person. It's already starting to happen. As we thought more transistors would be able to make it happen. Now we're not going to have more transistors. Can we still make it happen? Can we come up with a cure for cancer? Can we come up with a way to predict a tsunami before the tsunami occurs? Today, if we look at the data, we can predict the tsunami will come tomorrow. And the computer will give us that answer in 2 weeks. I don't have to wait 2 weeks to hear that the tsunami will come tomorrow. I just have to look out my window tomorrow, and there will be the tsunami. What I want is to predict the tsunami in 10 minutes so I can run away so that when it hits, I'm gone. These are the things that we need to do. We were hoping that more transistors would do it. Instead, we have got to act smarter. This is just a slide showing us the growth of inventions that have happened over the years since the first computer on a chip back in 1971. Now it's 2017. And if I had time, I would go through each of these elements one by one and show you the benefit that came because I had more transistors that I could use. I don't have time, so I can't. I will highlight a few of them. Pipelining is just a fancy word for assembly line. I remember when I was a boy, and my school, I was 10 years old at the time, they took me to a factory which was an assembly line for one of the American automobile manufacturers, Ford Motor Company. And what they did is on that assembly line, they put a chassis of an automobile at one end, and then for the next 2 hours, that chassis moved along the assembly line, and every 2 minutes, a different mechanic would add something to that chassis. One mechanic put on the wheels, another mechanic tightened the bolts, another mechanic hitched up the steering wheel, another mechanic connected the electrical. 60 mechanics working 2 minutes each. 2 hours later, a mechanic would drive the completed automobile off the assembly line. Now, if you were just standing at the end of the assembly line and watching the automobiles come off, you'd say, wow, 2 minutes to assemble a Ford. I remember the first time I came up with this analogy, one of the students in the audience raised his hand and he said, you know, I own a Ford. I believe it only took 2 minutes to assemble that Ford. But it didn't. It took 2 hours. But during that 2 hour period, there were 60 mechanics that were all working on cars as they were going across the assembly line. Now, in the old days, we used to process instructions in the computer by doing each step, and then the next step, and then the next step, until finally we're done. Then we do the next instruction, the first step and the second step. We fetch the instruction, then we decode it, and then we figure out where the data is, and then we get the data, and then we operate on the data. And then somebody said, what if we introduce an assembly line? Then we can be finishing these instructions very quickly because we have all the logic on the microprocessor taking part in the process all the time. Branch prediction. Some of you have written computer programs. Perhaps all of you have written computer programs. And you know what an if statement is. So if something is true, do this. If it's not true, do that. Well, I want to bring in these instructions. I want to bring in the instruction that says do this, or I want to bring in the instruction that says do that. Which do I bring in? Depends on what happened with the previous instruction. But the previous instruction goes along this assembly line. And there are many steps in that assembly line. So I don't know until the instruction gets to the end whether I next want to bring in this or bring in that. That's the essence of the if statement. If something is the case, which is a previous instruction, then do this. If not, else do that. So I want to bring in the this or that before I know which I should bring in. How do I do that? Driving along the road and you come to a fork. Should you go this way or should you go that way? Well, what you could do is stop the automobile, look at the map, figure it all out, and then go. Or what you could do is say, you know, I think I go this way, and just go. And then you tell your partner sitting next to you, check the map to be sure that I'm right. And then 15 minutes later, your partner says, you went the wrong way. So you got to go all the way back and all the way this way. But what happens if you can guess 98% of the time correctly? Then it's worth doing. Because most of the time, what your partner says is you're correct and you saved all that time. We don't call it guessing because nobody's willing to pay me a lot of money for guessing. We say predicting. That's nicer. And we call this way or that way a branch. So it's branch prediction. Requires more of these transistors on the chip. And as you look at that list, and I'll stop here with this list, but every one of those bullets talks about another step to make processing go faster because we have more transistors available. But now we're reaching the point where we don't have more transistors available. The von Neumann paradigm. It's a straightforward model of executing programs. As I said, I first have to get the instruction that I want to process. Then I have to decode it, figure out what it is this instruction is asking me to do. Then I have to figure out where the information I'm going to need to compute whatever this instruction is telling me to do. Then I have to go get that information. It's a step-by-step procedure, if you will, and it's done by an assembly line. And it's been around a very long time. Von Neumann came up with this back in the 1940s, actually. Many people will tell you that the days of the von Neumann machine are over, that it's dead. My take is that it is not dead, and it will live probably forever, certainly for a long time. And the reason that it will live forever is as people come up with these new things they want to do, if they were to operate by themselves with no control, we'd have chaos. You've been to a symphony orchestra concert. What if the instruments were playing their beautiful music, but there was no conductor in the room? Nobody to guide the instruments that they're playing together. We wouldn't have a symphony. We would have a cacophony. We would have noise. So what the von Neumann model does is controls all these fancy things that people come up with so they work together. So we will have the von Neumann model. Finally, before I get into my cases, is the transformation hierarchy. This is something I came up with 35 years ago, actually, when I was still teaching at Berkeley. Some people refer to it as a software stack, but it's not a software stack, as you will see in a moment, because it's not just the software. The transformation hierarchy takes all the steps, considers all the steps between somebody thinking about a problem in English, in Chinese, in whatever language you think in, and getting it all the way down to the thing that is actually going to do the computing, which are the electrons that move from one voltage to another. This transformation hierarchy, which I show you now, is going to be useful moving forward. And I noticed that this slide is, we had to transform my PowerPoint from one technology to another, and all the information that was inside between problems and electrons ended up getting tired of being inside. They wanted to go outside to get some fresh air. So you see them down the left-hand column. They really should be inside. In fact, is there a, yeah, there is. I don't know whether you can see that. So these things should be sitting in. So I want to take this and move it in here. But I'm a Jesuit university, and you're certainly able to do that yourself. The point is, a transformation hierarchy is about software and hardware. We have a problem, and it's in some natural language. It might be the command that you give to the computer because you're surfing the internet, because you want to find out some information. Or it may be the actual algorithms that actually do that searching. Or it may be the program that is executed to carry out that searching. Or it may be after that program in some higher level language. Could be C, could be Python, could be Fortran, if you're old like me. And the compiler translates it into zeros and ones of the ISA. The ISA. Or it could be the microarchitecture, the actual structures that carry out the work. Or it could be the actual circuits, the electrical circuits. I don't know how many of you have studied VLSI design. The algorithms that are in, I say I want to build an adder. Well, how do I build the adder? What do the circuits look like? Or it could be all the way down at the bottom, the actual electrons that do the job. And historically, what we've been able to do because of Moore's Law is not worry about the layers that we don't work in. So if we happen to design algorithms, we say, we design algorithms. We don't care about the problem. We don't care about the electrons. We only care about the algorithm. Or people like me, a microarchitect. What I do is worry about designing the microarchitecture which implements the zeros and ones that the compiler produces. I don't care how the programmer, what the programmer wanted to do. I only care about producing the ability to handle the zeros and ones. And I don't care about the circuits underneath. That's the circuit designer's job. My job, microarchitecture. And historically, each of us working in the field, and there are many of you in this room that will not be microarchitects. You may be algorithm people, you may be compiler writers, you may be circuit designers. And if you were older, you wouldn't have to worry about anything else. Because Moore's Law allowed you to focus just on your one area. But now Moore's Law is ending. What are we going to do about it? We'll see. What I've got is three cases. Case one is accelerators. There are many ways to implement this accelerator. I can actually do a VLSI circuit. We call it an ASIC. We design a circuit just to do this one thing that we want to do very fast. That's good for just this one thing. Can't change it at all. I don't know how many of you work as a mechanic on automobiles, but you have a wrench, and you want to use that wrench to tighten a bolt. And if the bolt is stuck because of the rust, because of the corrosion, you need a wrench that can really grab that bolt. And so we could use what we call an adjustable wrench, where we can work with the thumb and we can change the opening in the wrench. And I don't know how many of you have ever tried to do that, but the result is that it doesn't really grab the bolt as tight as it needs to be. Or you can have a wrench that's just that one opening, and it does grab it. The problem is that that wrench, if it's a fixed width that you can't adjust, it's only good for bolts of that size. So it's much better for the bolt of that size. It's no good for any bolt of any other size. Adjustable wrench, it's good for any size, but it's useless if that bolt is corroded, rusted into the chassis. So an ASIC is like a fixed wrench where it's only good for that one thing. Or I could use an FPGA, which allows me to have a certain amount of adjustability, gives me more flexibility, but it's not as fast, it's not as good. Or I can introduce in the control store some microcode, which I can have an instruction that accesses that microcode that can do the job much faster than just using normal programs. So these are all ways to implement an accelerator. And there are very important things that are on the horizon today that are accelerators that need this job to be done much faster. They're not computers, they're accelerators. Many people talk about quantum computing, and there will be a quantum computer which can solve some non-deterministic polynomial problem much faster. Won't be a quantum computer, it'll be a quantum accelerator. This quantum computer that people mistakenly talk about is not going to fetch the instruction and decode the instruction and find the data. This quantum accelerator, and there are already some of them being designed right now, we've got a long way to go, but when we get done, we will have an accelerator under the control of the von Neumann machine that will just do the actual computation after the instruction is fetched and decoded and the data has been supplied. Machine learning, which is, you all have heard about Dadian Now, for example. I could show off and write Dadian Now for you, but I will not do that. Da, you know, Dien Now, and the project that is in Beijing, and now they're actually at the second and third generation to do deep learning. Again, an accelerator that's going to do things faster under the control of the von Neumann machine. I give these two examples because these are the very hot topics today of what we want the computer to be able to do tomorrow. But you notice in red or in orange, I've said, in order to make these accelerators happen, I'm going to need the attention of the person writing the algorithm. The person writing the algorithm. I'm going to need the attention of the programmer who's going to take that algorithm and actually write C code or Python code or whatever. And I'm going to need the attention of the compiler writer who's going to translate that into the zeros and ones. And I'm going to need the attention of people like me that's going to take those zeros and ones and design structures that are faster. What's my point? That if we're going to have accelerators moving forward that are going to do things much faster than we've been able to do before, and we don't have the benefit of Moore's law, then everybody in this transformation hierarchy is going to have to do their part in making that happen. Number two case, multi-core, many-core. What the companies have done is, because it is too difficult to make a better branch predictor or a better out-of-order execution mechanism, what they've done is they put multiple cores, processes on the chip. It started out with, well, actually, it started out back in 1985, but those cores did very little interesting stuff. The size of the data was 1 bit. Not very useful, either a 0 or a 1. But I had many of them on the chip, so I could have the 0 or 1 for each of them contributing to the same number in 1985. Today, I've got 5 billion transistors. So people are talking about having 1,000 cores on the chip, 1,000 processes to solve a problem. How do I program them? In order to take advantage of the multi-core and many-core chip of today even, let alone what we'll have tomorrow, we need to be able to program them. And we are in the infancy of being able to program 1,000 processes on a chip. What we're going to end up seeing, if we don't think smarter, is these 1,000 processes on the chip, and one of them is solving the problem, and the other 1,000 minus 1, they're sitting there doing nothing. Requires the programmer to take advantage and write the program that can actually exploit all these. And the final case is spatial computing. It's a very domain-specific instance. If you have a problem where the program is very small, but you want to run that program on a huge amount of data, then if I can take that program and convert it to a data flow graph and pass that data by it, I can get the advantage of all the operations in that data flow graph working all the time. We already have companies that are starting to look at doing that. We call it spatial computing because instead of having a program, I've got a data flow graph that I'm passing the data through the data flow graph. But look at the orange at the bottom. If the software can produce the data flow graph. Moore's law ending means no more faster transistors, no more increase in the number. We won't even be able to have them all on at once. We've got an enormous energy problem so that even today, we cannot have all the transistors on the chip on at the same time. We call it dark silicon. It's like some of these countries where you can put the electricity on in your home on Monday, and somebody else on Tuesday, and somebody else on Wednesday, and the rest of the week, no electricity. Sit in the dark. So we call it dark silicon. The transistors can be on some of the time, other transistors some of the other time. Who decides when each go on? The higher levels of the transformation hierarchy. We will have von Neumann, and we will have accelerators. We'll have to design smarter so as to know which transistors to turn on and when to use this enormous number of transistors that we will have when Moore's law ends. That will mean bringing to the table those working at all the levels of my transformation hierarchy. So now, what are we going to do moving forward? How are we going to make this happen? How are we going to get everybody at this different level of the transformation hierarchy able to contribute to the solution when we're no longer going to have faster transistors and we're no longer going to have more of them on the chip? What must happen in order for us to be able to engage everyone? And you're at a university, and the university is the answer. It's all about education. Unfortunately, in most universities, education gets in the way. Students start with Java. I'm happy to say not here, but students start with Java. Students don't get it. There's no way you can write a program in Java and know what's going on underneath. They don't have the underpinnings. They don't know how the computer is actually processing their Java. Objects, which have been advertised as being beautiful, I don't have to know what's going on underneath. It'll take care of itself. Objects are too high a level of abstraction to start with. So students end up memorizing. Memorizing isn't learning, and certainly not understanding. Or Students are hardware people or software people. I'm a hardware person. I'm a software person. Very few of them are just people. And those who think of themselves as a hardware person or a software person exclusively and disregards the other area, they will be left behind, because we're not getting more transistors and we're not getting faster transistors. Here at your university, we have a course enabling students to understand at the early level, freshman level, more than one layer. We get rid of the notion of objects first. We start with how the computer works. We call it motivated bottom-up. Students build on what they already know, starting with the transistor and how the transistor works. Memorizing is replaced with real learning because you're building on what you know. Continuing to raise the level of abstraction. There is no question that the higher the level of abstraction a person works at, the more productive that person can be. But it only works if they understand what's going on at the underlying layers. The student sees all the layers from the beginning because the student is going from the transistor to the circuit, to the microarchitecture, to the instruction set architecture, to the code, to the program, to the algorithm, and every step of the way building, not memorizing, on what the student already knows. And then the layers get broken naturally. And so even though the student is working at one of these layers, the student knows the layers below and the layers above. I've been doing this with freshmen since 1995. I've been doing this here with Professor Jung since about 2011, I think. We start with what they know. The transistor acting like a switch, and everybody in this room knows how the switch works. You go into a room, it's dark, boom, it's light. And you know that, and you know why. Transistors just do that. The microprocessor, even though it has 10 billion transistors, they all look like wall switches. And we build out of wall switches more sophisticated stuff. I chose a computer that is simple but not too simple. As Albert Einstein once said, it's important to get as simple as possible but no simpler. That is, go as simple as you can while still retaining the richness of the concept that you're trying to get across. And the students continually build on what they know, raising the level of abstraction, memorizing as little as absolutely necessary, trying very hard to not introduce any magic. The motivated bottom-up approach, which I use. I start with an overview of what computing is all about. And then I talk about operations on bits and bytes. And then I talk about the transistor. So I'm motivating, and I'm motivating, and now I'm teaching. And from the transistor, digital logic, and then to the finite state machine, the von Neumann model that controls the processing. And then the computer, and the little computer that I've introduced, which I call the little computer number 3. Why number 3? I got it wrong the first time, and when I fixed it, I hadn't really fixed it. Now I think I fixed it. And then I'm ready for programming and debugging. Then I talk about assembly language, and data structures, and I/O. And then I'm ready for a high-level language. And I talk about programming in C. And so I motivate, and I motivate, and I motivate, and then I teach. Then I motivate, and then I teach. And the student learns, and the student understands all the layers. I've been doing this since 1995. Here's a picture of memory, which the student understands how it works, the decoding of the address, the storage of the bits, the multiplexing of the different words. They understand that after 3 weeks into the course. Here's the instruction set of my little computer. Fits on one page. Doesn't take a book that's as thick as a telephone directory. The data path, which is the structures that go into processing the information. Not very complicated. the state machine, which controls, the von Neumann machine that controls all the processing. Again, not very complicated. And doing it this way, we get rid of magic. We minimize memorization, maximize understanding. Students build on what they know. That's the hallmark of this approach. They debug their own programs because they can. Students end up with a broad-based foundation encompassing the entire transformation hierarchy. And so as we move forward and Moore's Law ends and we have no more transistors available, all those orange that you saw on each of these cases enables people to contribute to the solution of problems. I can do machine learning because the person doing machine learning understands all the layers of the transformation hierarchy. Most importantly, when we do this, we turn out graduates who can design algorithms, write compilers, operating systems, specify architectures, design microarchitectures. Graduates who understand the layers and can break the layers and, in summary, design smarter and therefore continue to improve computer technology, even in the face of Moore's Law coming to an end. So I say Moore's Law, is it something that you say give up, discourage, all you dreamers who want to use better and better computers, we're done, forget it? Or is it an opportunity to learn all the layers so you contribute to continuing to have this capability, even though we won't have Moore's Law being able to help us do it? We'll have to do it ourselves by understanding all the layers in the transformation hierarchy. Sheshe.
Or electrical engineering. So if you want to do a good job in the future, so in the future that the Moore's Law being the end, so you have to know all the levels, how the levels work in its way, right? So after you know the details, know how the levels work, then you can break them down and to use new technologies to make it faster, right? So let's give a great thankful applause. And I think the next session is questions and answer. So whatever questions you want to ask about the lecture, about the contents in the lectures, or about anything you want to know to study in the university, or how to plan your career, anything, okay?
Are there any questions? Nobody wants to ask the first question, ever. I've been doing this for a long time. We have somebody who's good.
As we all know that nowadays we use many cores to integrate them in one chip to do some acceleration. And besides CPUs do.
I cannot hear you. You have to speak up.
And what do you think the kind of acceleration chips are named many integrated cores?
So I'm not understanding the question. Maybe it's better if he asks you the question in Chinese, and then you translate it for me? Would that work better?
What do you think of MIC, many integrated cores, this kind of accelerators?
What do I think of?
MIC, like Intel Xeon Phi accelerator.
MIC?
Yes,
I don't know what MIC is. Tell me more.
many integrated cores.
Many integrated cores. Many cores.
对，就重核加速卡，就重核，对。
Many integrated cores.
对。
So you
It's-
you speak about the many core processors, right?
Right.
So he talks about many integrated cores.
Yeah, so I had never heard the term many integrated cores. However, the many cores that I talked about are all on that same chip. So apparently somebody has taken that concept and given it the name many integrated cores.
Yes, it's a term that invented by Intel.
Oh, Intel. So that's the problem, is that we have people at Intel like me doing the work, and then we have people at Intel making up nice fancy names for what the people doing the work are doing. So I had not heard this, and I will have to talk to my friends at Intel and say, why are you confusing them with fancy names? The word integrated simply means that everything is on the same chip.
Yes.
And so when most of us say many core, we are assuming that the listener understands that all those cores are on that same chip. So I could have said, and maybe I should from now on, thanks to the marketing person at Intel, I should say many integrated core. So the problem, as I said on the slide, in fact, maybe I can bring it back up. We need to figure out, see, in the old days of the overhead transparencies, I didn't have to do all this silliness to get back to where I was. You see the bottom line? We still, so multi-core, many-core. The term multi-core was first given when we had two on the chip.
Yes.
See, most of the early, in fact, I have in my pocket, you see this? You know what that is, of course. It's actually a keychain. It's a way to keep my keys together. The chip failed its electrical test, so it couldn't be put into a laptop. On this chip is one core, 1992, Pentium. Then they, at Intel and other companies, decided to put two. So two is more than one, multi-core, and then 4, and then 8. At some point, they said, you know, I've got so many cores that I need to differentiate it from multi-core. So they call it many-core, perhaps 32. Today, we've got chips with 100 cores on the chip, integrated, as you say, all on the same chip. But look what it says. I still have the problem, how do I program it? How do I write a program that can take advantage of all these cores? And we're not there yet. A lot of people are working on it, but we're still not there yet. What's it going to require? Somebody who understands the transformation hierarchy, wants to write algorithms to take advantage of all these cores on the chip, so it has to understand what's on the cores on the chip. You know, there's another part of what I could have added to the talk, except that I was afraid, as I said, that the talk would end up taking 3 or 4 hours, is that if I have many cores on the chip, how are they connected? That's another problem. Are they connected on a bus, so they're all connected to the one bus? In which case, I can only do one thing at a time with a bus. Are they connected in a ring? Are they connected by some other network? if I'm going to program for many core, the more I understand in the microarchitecture, which is how they're connected, the better job I'm going to be able to do on this many integrated core chip. Okay? So there's no question that the many integrated core chip is here today.
Yes.
But what's important is not that there are many cores on that chip. What's important is, are they all being used? Right? If only one of them is being used, why are the others all on the chip? What good are they doing? Right? So I did not realize that Intel had introduced this term, many integrated cores. What's important is, how do we program the chip that has these many integrated cores? And that's something that many of you will probably be involved in making happen. Does that answer your question?
No. Not exactly this. Actually,
Go ahead.
my question is, they appear as a accelerated card and maybe 60 or about 100 cores could be integrated to one chip, and they are made into a type of device like GPU to perform perform as an accelerator.
So there's an echo that I'm not getting all of this. So you said there's 50 or 100 cores on the chip.
Yes.
Okay, and?
What do you think of this kind of device compared to GPU as an accelerator?
Very good question. So the GPU is an accelerator. It's not a computer.
Yes.
It's an accelerator.
Yeah.
Right? So the GPU, in order for the GPU is made up of, first of all, several processors, but there are several accelerators. And each one of them is operating in what we call SIMD mode, which means it's the accelerator itself is broken down into multiple lanes, all doing exactly the same thing. Before the GPU can do what it has to do, the von Neumann model has to fetch the GPU instruction, it has to decode it, it has to get the data, and then it provides the data to the GPU. And now the GPU can operate on that data very, very fast. But it's just an accelerator. So, in fact, I could have had case 4. I gave you case 1, 2, 3. I could have given you case 4, the GPU. It's another example, but it's an accelerator and requires a von Neumann machine to do the fetch and the decode and all that other stuff. So your question is, okay, how does a GPU compare with CPUs? The CPU is the von Neumann model. Moving forward, if you understand what the GPU can do and how it does it, and you understand what the von Neumann model does and how it does it, then you can write your algorithms to take advantage of the capability of the GPU, which is working at the, at the request of the CPU. So I don't see it as either or. I see it as both. The CPU that's controlling the processing and the GPU that is doing very, very fast that piece of computation that requires the capability of the GPU. If you've been following some of the discussion that's been going on, there are people that say, GPU. Other people, no, CPU. The real answer, both are necessary. Okay?
Okay, thank you.
Thank you. Question?
So ladies first, huh?
Ladies first.
Thank you. Thank you,
That's an
Professor
old
Pat.
style. Now we need men first, see?
I'm kind of feminist, actually. Okay, so I have to first clarify that I'm not a student here. I'm actually still a 12th grader in high school. And I'm very interested in the idea of knowing the different layers of hierarchy, but I'm like recently, or for now, I'm actually trying to find the online courses or
Are you trying to
textbooks.
find what?
Online courses or textbooks, because those are the only things that are available to me. But for the things that I can find, they're either a hardware only or a software, like programming only. And I'm wondering, do you have any suggestions for incoming freshmen to how, like, where can I start if I want to learn about the different layers or like various layers of the hierarchy? Thank you.
Did you set up that question? Did you tell me you're still in high school right now?
Yep.
You're in high school right now? Yeah. So the answer is very simple. The only question I'm doing is, should I give you this answer, because it's a little self-centered, and if I give you this answer, then why not? So the answer is my book. And I wrote the book specifically because of the question that you asked. And you're absolutely right. It's very difficult to find a book that will do both and show you this progression. And so that's why I wrote the book. When did I write the book? In 1995 is when I first started writing it. And I've gotten many professors from universities, when they see the book, they say, boy, I don't know why you would want to waste your time writing a book for freshmen, but I'm glad you did. Because the focus of our book, and you can get that book both in English and in Chinese. I don't know, maybe you don't speak Chinese. Maybe you prefer having it in Spanish. It's also in Spanish. It's been translated into Chinese and Spanish. And the good news is the advantage of being Chinese rather than American. If you buy the book in the U.S., it's very expensive. If you buy the book in China, it's very inexpensive. There is a company here in China that produces the book both in English and in Chinese, and I don't know what the cost is, but it's a lot cheaper than it is in the U.S. And it does exactly what I've said today. I wish more people would do this. I did not write the book to make money. In fact, I tell students all the time that if you can steal the book rather than buy the book, steal the book, you know. Or borrow the book from somebody who used the book before you. Because I really don't care about the money. I care about the concept. And the concept, unfortunately, so far, has not been, there are about 100 universities that are using the book. But there are about 5,000 universities that are teaching Java. So I have not won the war yet, but every year a few more universities are recognizing that it's important to understand the transformation hierarchy if you're going to be successful after you graduate. And that's what you want, is to be successful after you graduate. You know, the word for graduation in English is called commencement. And the word commencement means beginning. So what we do in the university is we prepare you for the beginning. And if you're going to be prepared, you need to know both. And so far, my book is pretty much the only one that does it. But I am hopeful that other authors will do the same thing, so that if an author wants to write a book on software, he will, or she, in fact, it'll probably have to be she, because men are just too stupid, she will include enough hardware so that you get both. But right now, we teach the course during the summer here when are we doing it? In July this year, yeah.
July 3rd to July 20.
So we are doing it here this summer again. But someday I hope, like you, that it will be not just in my book, that other authors will do both. Because you really do have to understand both. Okay?
Okay.
But,
He has to go.
I had to.
I know, I thank you for sticking. So this is an administrator, executive vice president, but he also cares about wording.
Thank you. Point about yes.
Question?
I want to question that you say the limitation of the future computer will be the development of the CPU, but I think in reality, the input and output may be more limited than the frequency of the CPU.
I'm not understanding what you're asking.
I think in the engineering that if you run a program, most of the time you consume to wait the input or the output from memory for hard disk from the network. So in fact that the limitation cannot be the at most the limitation is not the CPU. Is it possible to reduce some speed of the CPU to add some more complex instruction in CPU to reduce the waiting time of the input and output?
So you want to help him? Go ahead. So I've got the notion that his point is that there's so much energy put into the CPU and making it faster that the real problem becomes the memory and the network. And that's absolutely correct. But now he wants to what? Slow down the CPU?
No. Because the development tendency of CPU is to make it faster and to contain less instruction in the less instruction in their ISA. And is there in future
contain fewer instructions in the ISA. Right.
But you know, if you have a more complex ISA, more complex ISA.
So you're running much too fast. My English is not as good as yours. Talk slower so I can understand what you're saying.
Actually, he said that is that good to design more complicated instructions to help the input output, so that when we wait for the slower input output, then we can do some complicated instructions.
So
yes,
I'm not understanding.
Of course, he said the CPU is so fast.
I understand the CPU is so fast.
He wastes a lot of time on waiting the input output. Right?
That's certainly true.
Yeah.
And so there are.
We not design some complicated instructions to do more functions.
So he wants to not design the complicated instruction?
No, we can. He said, he suggested.
So we want to design more complicated instructions, right?
So that when we're waiting for the IOs,
Right.
then we can run in the complicated.
So we already do that. And in fact, I agree with you.
do you think
that we
it's a tendency in the future of the development of the CPU?
So now you're talking too soft again. So in the future, what?
In the future, is the more complicated ISA will be the future of the.
Okay, so I think what you're getting at is what will the instructions look like in the future, and will they be more complicated or will they be simpler?
Yeah.
And you correctly recognize that a more complicated instruction can do a lot more computation while it's waiting for the memory and I/O. And that's absolutely correct. We have had a group of people suggesting over the last several years this notion called RISC computer, where the instructions could be very simple. And I think most of us who are serious microarchitects recognize that that's not a good idea. Your idea is the better idea. Why? Because if you have a simple instruction, it takes a lot of instructions to do the same piece of work. So each one of them has to be fetched and decoded and figured out where to go and get the data and put the data. Then the next instruction has to come and take the data. If I have a complicated instruction, then a part of that instruction can do some computation, and then instead of putting the data and having the next instruction get the data, what I can do is have the first part do that computation and send that data to where it's needed by the second part. We save a lot of time. What is going to happen, in my view, moving forward, is what I said, accelerators. So these complicated instructions that you're talking about will be accelerators. They will do a complicated piece of work much faster than I can do it under program control. Something you might not be aware of is that when I go to memory to get data, it takes a certain amount of time to go to the memory and get the data. It turns out that we've shown, and we've actually published this about a year and a half ago, that most of the time, we refer to the time I go to the memory to get data, it takes a certain amount of time. We call that time the latency. And it turns out that more than half of that latency is not in going to memory and getting the data back, but it's all the things that are going on in the chip before you can send the request out to the memory. So at the microarchitecture level, in the CPU, if you want to separate the CPU from the memory, a lot of time, even in going to the memory, more than half the time is spent in the CPU. It's also true that I/O is incredibly slow compared to the memory and the CPU. So what we're going to require, and in fact, requires the attention of the person writing the algorithm, the programmer, requires everybody to organize the work so that I can be doing that computation fast while I'm waiting for the I/O. There's one more point that's worth mentioning, is there are really two different kinds of applications on computers. You probably have one of these in your pocket. I'm not going to be able to ever predict a tsunami with one of these, okay? This is very I/O intensive. Most of the time with this, I'm waiting for I/O, because the value of this is a human interacting with it. And humans are slow, computers are fast. But the other part of the problem, which is a tsunami, or curing cancer, or doing a lot of computation very, very fast, also has the characteristic that it's not waiting for I/O. So improving the computation and the access to information, that is to say the memory, or over the network, can be, if I organize the problem, the person writing the algorithm properly, I can make the whole thing go a lot faster. I don't know whether that helps or not.
Thank you.
Okay. Professor Jung, you've got to, they don't need you anymore. They can,
Professor, first I'll try my best to state my problem clearly. We are focusing on improving the performance of computer. So then we have multi-core, multi-thread, multitask, doing multitask in parallel. We even use GPU to compute. All we've done is to improve the computer performance. In other words, it's to build a higher performance supercomputer. but it just do more things in one computer. Why we do many things in multi-computer? There's the supercomputer is costly. We spend a lot of money to build a supercomputer, but there's many ordinary computer like the personal computer. Then we can gather them together to do the compute task. Then we'll get more compute resource. So my question is how to coordinate these computers and make them work together to do our task.
So the answer is right up here, right? The person writing the algorithm, the programmer.
But the question is not.
No. So let me try to deal with it. I know what you're asking. So what he's saying is that if one was to buy a supercomputer, the cost is enormous, very huge. But the benefit is that I can get a problem solved much, much faster. And he says, why don't I solve my problem during the vacation of the university when all the students are gone, so all those rooms we have in the university campus, we have all those little computers, they're not being used. I will take my problem and I'll work it in such a way that while everyone else is on vacation with their mother and their father and getting fat from their mother's cooking, what I will do is I will use all those computers on the campus to solve my problem. That's what your question is, yeah. And the first time I thought of that was about 25 years ago, teaching at the university, and seeing all the undergraduates go home for, in the U.S., Christmas vacation. I said, why don't I use all those computers that are in those empty rooms to solve my problem? And you're absolutely right, that it would be much less expensive. Because if I have 1,000 computers and they all cost $100 each, that's 1,000 times 100, that's a lot smaller than $20 million, dollars for a supercomputer. You're right. What's the problem? The problem is what I say up there. I first have to take my problem and break it down so I can actually be using all these little computers at the same time. I also have to break it down so that the communication between these computers is correct. So that if this computer is doing something and it needs a result, it produces a result that's needed by that computer, it can send the result in a timely way. I'll give you a very simple example that I give to my freshmen. I say, supposing I want to compute 10 factorial. You understand the mathematical concept factorial? Yes. Okay. Supposing I tell you that the only thing that matters is how long it takes to multiply. So I will say it takes 1 unit of time to multiply two numbers, and it takes 0.00001 units of time to do anything else other than multiply. Okay? You understand my formulation of my computer?
Okay, I understand.
I've got instructions to multiply two numbers takes 1 unit of time. To add, to branch, to load, to store, everything else takes 0.00001 units of time. So the only thing that matters is my multiplying, right? How many units of time to compute 10 factorial?
Nine multiplication.
So you see what he's done? He's multiplied by 1. You said 10 times 9, that's 1, times 8, times 7, times 6, times 5, times 4, times 3, times 2, times 1. 9 units of time. One of those multipliers was not necessary. Which one?
Times 1.
Times 1, that's right. So the correct answer is 8 units of time, right? Supposing I had 2 computers, how many units of time?
If they can work together, 4 of each can do 4.
That's very good, very close. Not exactly, but you see so he's very intelligent. He sees the way to do it. What he says is, what I'm going to do before I start is I'm going to say, hey, computer, I want you to compute 5 factorial. So that computer does 5 times 4 times 3 times 2, 3 units of time. And while that's going on, he does 10 times 9 times 8 times 7 times 6, 4 units of time. This is already done because it only took 3 units of time. So then what he does is multiplies this by that, 5 units of time. So instead of taking 8, it only took 5. And you're absolutely right. If I have 2 computers, and I know that I can tell that computer to do this part of the job, compute 5 factorial, while I'm doing the rest of the job, and then give me the result. Now there's an example of a very simple case. Computing 10 factorial. And my experience has been that if I were to give that problem to everyone in this room and say, okay, it takes 8 units of time. How about if I have 2 computers? Can I do it faster? My experience in the U.S. has been that the number of students who would be able to say it only takes 5 units of time is not a large percentage. Now that's just a very simple problem, 10 factorial. What you would like us to do is do this same thing on a much more complicated problem and do it on a whole room full of simple computers. And that's the objective. It requires somebody to understand how to make all these computers work together, the interconnection, the sending of a result from here to there, all those things. This will happen. We're not there yet, but we certainly will be. And it's going to require students like you understanding all the layers so that the person writing the algorithm understands how the computers themselves will talk together. Okay?
Thank you, Professor. Thank you.
Hello, Professor Fett. In the great speech, you have talked about the end of the Moore's law and given us 3 cases like accelerators or the many core to solve the problem it brings. However, we have heard the breaking news that a quantum computer, absolutely have heard it, has been successfully designed by the Chinese researchers. What I want to ask is, can we describe the quantum computer as a case for to solve the problems that the Moore's law is ending?
So, first of all, there is no such thing as a quantum computer.
Why?
Because what a computer has to do is take a program and fetch the instructions and decode the instructions and figure out where the data is and go get the data and then process the data and store the results. And the quantum computer doesn't do that. What the quantum computer does is the computation step within all that has to go on in order to make the result happen. So when people say a quantum computer, they are misstating what is going on. It's a quantum accelerator. You see the bullet up there, examples, quantum computing and machine learning. Those are 2 examples of the computation itself that assumes that the instructions have been fetched, that they've been decoded, that I've got the data, and now I give the data to this quantum thing, which I would rather call an accelerator, since it's only doing one piece of what a computer does. Now, as far as, I don't know who says they built a quantum computer, the truth of the matter is they haven't even built a quantum accelerator yet. The concept of quantum computing, in fact, the reason for the word quantum is because it's a cool term to use. Because in physics, we talk about quantum physics and Heisenberg's principle and this Schrodinger's cat. The cat is dead and the cat is alive at the same time. You understand that? If you understand that, you're smarter than I am. In fact, one of the great American physicists of all time, Richard Feynman, said, anybody who thinks they understand quantum mechanics doesn't understand quantum mechanics. Nobody understands it. But what we've been able to do with quantum mechanics is describe it mathematically, and the behavior that we see agrees with that mathematics. So therefore, we believe it. But understand it? Professor Feynman, very famous Nobel Prize winner in physics, says anyone who says they understand it really doesn't. If he says that, I believe him. I certainly don't. The concept of being dead and alive at the same time has introduced for the quantum computing people the concept of a qubit. Now, you've studied computing, you understand bit. A bit is either 0 or it's 1. In quantum computing, it's both at the same time. How can you be both 0 and 1 at the same time? What the physicists have shown is that what we can do with our various techniques in the physics is take a number of these bits, which we call qubits. Each one of these bits is 0 and 1 at the same time. Well, really? Well, it has a propensity to be 0 or a propensity to be 1. But we can apply physics to this set of bits. And instead of having each bit be a specific value, let's say I have 4 bits. I could have 0, 1, 1, 0. That's one condition. That's one case of the 4 bits. Altogether, there are 16 different cases. What quantum computing is suggested to be able to do is if I have a problem and the solution is 4 bits, using this quantum accelerator, I can work on all 4 bits having all 16 values. This is both a 0 and a 1 at the same time. Really? Well, sort of. This is a 0 and a 1 at the same time. Really? Sort of. So instead of having one of the 16 cases, I've got all 16 cases, which I will work at driving toward the actual one case that it's supposed to do. In the field of computer science theory, we have this concept called NP completeness. NP completeness, the N in NP completeness, the N stands for non-deterministic, which is to say, so NP means non-deterministic polynomial. The non-deterministic says that I don't know which of the 16 it is. I can assume that I'll pick the right one. How are you going to do that? We don't know. I'll give you an example of a simple problem. Supposing I'm a salesman and I have goods and I want to visit Beijing and Nanjing and Hangzhou and Suzhou and Chongqing and Xi'an. And I want to go to each of these cities to sell what I'm selling. The traveling salesman problem says, in which order should I be visiting these cities? So, for example, would I go from Hangzhou to Xi'an, and then from Xi'an to Suzhou? That would be fairly silly. I probably should go from Suzhou to Hangzhou, then to Xi'an, right? Because it would be less travel time. So the problem asks, how long would it take, minimum time, to visit all these cities, each one once? Supposing I have 50 cities, not the 7 or 8 that I mentioned. Then I've got 50 factorial different paths that I could do. How long would it take? Forever. I wouldn't be able to be a salesman because I'd be sitting in my home figuring out the 50 factorial paths. So what quantum says is I non-deterministically pick each city correctly, and then I can just add them up. If it's 50 cities, it takes 49 adds. Now, but it only works if I guess correctly each step of the way. How am I going to do that? I have no idea. What quantum computing says is, since each city, the distance is this bit pattern, and I can have all bit patterns all at the same time, I can just add them up. I say, really? I don't know how to do that. Quantum computing says that we're going to be able to do that. And I agree, because I listened to the people working on it, that at some point in time, we may be able to make that happen. But it'll happen only for these very specialized algorithms that require a quantum accelerator to be able to do. And what I'm going to need is a large number of these qubits. And this company that you talk about, that they built a quantum computer. First of all, they didn't build a quantum computer. They may have built a quantum accelerator. So I don't know this company you're talking about. How many qubits do they have in their quantum computer?
I believe it's 4.
4, yeah. And they need 1,000. So they got a long way to go.
Yeah.
And eventually, I think they will develop. In fact, we've got companies in China, we've got companies in the U.S. I'll give you the name of a company that's building one right now. You may have heard of the company. They're better known for their operating system called Windows. The name of the company is?
Microsoft.
Microsoft, that's right. So in Microsoft, in Seattle, Washington, in Redmond, Washington, there is a group under the leadership of a computer architect who I know very well, who I admire greatly, is building a quantum accelerator. It will work when they get to be able to build a piece of hardware that has enough qubits that they can actually make it happen and put together all the stuff that's needed. Once they're done, what they will have is an accelerator that will require a von Neumann CPU to make it actually work. Okay? Right. Go ahead.
Quantum sounds such magical, but I still have a question.
I'm sorry?
If we can turn the questions into mathematics, then can we use the quantum computer to solve it? The most questions.
I'm sorry?
If we can turn the most questions into mathematics questions, can we use quantum computer to solve it?
So it's really the other way around. It's really that the mathematics, or so far, what's going to happen in the future, I have no way of really knowing. But so far, this quantum accelerator has been introduced because the mathematics would take too long. Have you taken a course in theoretical computer science where you have studied NP completeness yet? I guess not.
No.
So one of the biggest reasons why many people are interested in quantum computing is because there is an NP-complete problem, which is take a number very big number, which is created by multiplying two very large prime numbers together. So, for example, I'll give you an example of a number, 35. Now, if I tell you that 35 can be created by multiplying two prime numbers, you would tell me those two prime numbers are what?
5 and 7.
Right, 5 and 7. That's correct. Now, if I tell you that instead of saying 35, I say 753,621,342,718.
I don't know.
That's right. So the prime factorization problem is an NP-complete problem. It says, in order to be able to take that very big number and break it down into the two prime numbers that multiply together will give you that number, that is an NP-complete problem, and the mathematics is such that it's going to take a very, very long time. The reason why it's important to be able to solve that problem is most of the cryptography that goes on, PCP, for example, pretty much all the cryptography that goes on is based on the ability to be able to take a large number and break it down. Now, if I gave you two prime numbers, and they're very big, and asked you, can you multiply them? You would say, sure. I learned that when I was this big. But you can't go the other way. So if I say 35, you say 7 and 5. If I said 7 and 5, you would say
35.
35. It works because 35 is a small number. But if I take a very big number, I can't break it down. But if I give you the two pieces, you can multiply it. So all the cryptography that goes on works because it's easy to take two large prime numbers and multiply them. It's essentially impossible because it would take far too long to take the big number and break it down. The mathematics doesn't work. It takes far too long. So what people have said is, if I can solve this quantum computing problem, then I don't need the mathematics. I can do it with this quantum accelerator. So the effort right now is to take a problem where the mathematics would take too long, and instead, can I build a quantum accelerator that will allow me to do it? And so far, you say this company has 4 qubits, another company says 5 qubits. Both have a long way to go.
Yeah.
Okay?
Okay.
Okay,
Thank you.
good. Good question.
Well, Professor Pat, I'm continuing the previous student's question. I have a question on the mechanism of the quantum accelerator unit. It's basically, how does it work? Does it provide like 8 answers to the CPU simultaneously?
No. So you're asking the wrong guy. I'm not a physicist. I am told that it doesn't work on the 8 answers, but rather that it works on some tendency that as you do more and more, that tendency eventually works into each bit, either becomes a 1 or becomes a 0. How the circuitry actually makes that happen, I don't understand, frankly. And but there are people who do. I encourage you to find them. Most people working in quantum computing actually don't understand how it works, but they continue on. How the actual values end up working toward a solution, which is now a discrete solution, because now at the very end, each bit has to be either a 0 or 1. In the creation of that bit, as it goes through the process, the various circuitry elements actually keep adjusting until finally you get a 0 or 1. But the implication from the beginning is that that bit, that unit of storage called a qubit, is both a 0 and a 1 at the same time. And that's beyond my ability to understand it. How it works, I'm the wrong guy to ask.
Well, really, Sam, my previous understanding of that question is rather vague, and now it's a little bit clearer. My second question is concerning about your philosophy of constructing an undergrad course system for us. Though I'm still in high school, but I'm attending a university in America called Berkeley, and now they have, I learned that you've stayed in Berkeley for over 10 years, in the 80s, I guess, but now they have a program called EE and CS. That seems as adoption of your philosophy that combines the most basic from the bits to the all the way along high to the hierarchy, and finally on to the C and more advanced abstract program language. How would you comment on this? Has they been initially have been driven by your idea when you were here, or they gradually adopted your philosophy to require all the freshman students and all to the seniors?
Yeah, at what school?
Skills. Cal.
At University of California, Berkeley.
Yeah.
Yeah, so I would like to take credit for that, since I taught at Berkeley for 10 years back in the 80s. But I don't deserve any credit for that at all.
That's not possible.
And in fact, I'm not convinced that you studied at the University of California, Berkeley?
I'm gonna to.
I'm sorry?
I'm gonna to.
Oh, you're going to go to Berkeley?
Yes.
Yeah.
I'm curious about why they developed an idea of setting up such an incorporated program.
Yeah, so to be completely honest, the department is called EECS, and it was driven not by listening to me and saying, wow, Professor Pat has the right answer, we will follow him. It didn't happen that way. The way it happened, and this happened back in the 70s actually, there was an EE department and there was a CS department. And there was somebody up above at a higher level that said, why do we have two departments? We should have one department. And the EE people said, look. And the CS people said, look. And the person at the top said, do it. And so they combined the two departments. It's not just at Berkeley, by the way. Michigan is the same thing. MIT is the same thing. It's one. And in all cases, it was driven by the recognition that they shouldn't be separate, they should be together. Now, at my university, they're separate. In fact, they're in different colleges. So you understand that a university is made up of different colleges. So you have a college of science, you have a college of engineering, you have a college of business, you have a college of law, and EE at my university is in engineering, computer science is in the College of Science. So it's really separate. I agree with you, it should be together, and if it's together, you can have more of this that I talked about today. It was driven not by this recognition, but rather by somebody at the top saying, you will combine. It is possible, actually, to get a degree at Berkeley without embracing both. And I think that's unfortunate, because they have the capability to enable you to do both, and I hope you will when you get there. But one could graduate from Berkeley without getting both. But the opportunity to get both exists, and I hope you take advantage of it.
My point actually is, from Berkeley, how do you think the program of most ability of providing the harsh academic environment today?
So I'm not understanding part of your question. From my point of view, what?
How students, after undertaking such a rigorous program, would be enable a better survival chance in the harsh academic and career environment?
I'm still not understanding the depth of the question. How students will...
Well, take advantage of this program, how they will grow stronger, how they benefit from your philosophy, that's hierarchy of structure.
They will do better in everything if they have this foundation. There's no question about that.
So in your projection of the field, all things will come to an integrated and comprehensive utilization of all the concepts down to the hardware and up to the software.
So if you have the benefit of, so for example, the course that we teach here during the summer at Zhejiang University, if you have that course first, when you then take course, I'll even do better. At Michigan, when I moved from Berkeley to Michigan, and I saw that the professors were very upset with the students because they were trying to teach them a simple concept called recursion. The students couldn't understand it. They were trying to teach them a simple concept called pointer variables. Students couldn't understand it. So what I told the faculty at Michigan was, I want to teach my model first. Then you teach them recursion, and then you teach them pointers. And the faculty came to me afterwards, after doing this, so that the students started taking what I've told you about today. Then they took the course in programming. The professors came to me and said, it's amazing. I was able to teach them pointers in 1 minute, as opposed to 2 lectures and they still don't understand it. I was able to teach them recursion in 5 minutes after I taught them functions, because recursion is a special case of function. The professors in the logic and the computer hardware course came to me and they said, the students understand much better because in the first course they understand the foundation of the whole hierarchy. Now they can use that to understand better how to design the hardware. So the data is there, that if the student has the foundation first, they will learn better, more effectively, the stuff that comes later. As I said, there's only about 100 universities that are doing it my way. To my knowledge, there are 2 universities here in China that are teaching my course. There are several in India. There are universities in the U.S. Cornell University decided to adopt my way. Wisconsin does it my way. Illinois does it my way. I just found out recently that the #1 university in Greece, it's called the Technical University of Athens, they do it my way. So the data is there that if the student is provided with this model, everything that comes later makes more sense because the student sees where it fits within the transformation hierarchy. But, you know, there are 100 universities doing it this way. There are 5,000 universities that start with Java. So I've got a long way to go before I convince everybody. So you're going to help me do that at Berkeley, say?
Probably, thanks.
Okay.
I just want to hear more anecdotes that could reinforce the theme that we should build a hierarchy and more emphasize on the comprehensive hierarchy when we self-study all the computer science and electrical engineering stuff. Thank you, sir. Really, thanks.
Yeah, the data is all anecdotal. I don't know that I have a proof, but at some point you have enough anecdotal data that you say it works. Okay.
Any questions?
We have one here, and we have one way up at the back, and okay.
Hi. I just had a bit of a more general question.
Somebody who speaks English like an American, huh?
Well,
from the U.S.?
I'm Canadian, actually.
Canadian?
Yeah.
Canada is a good country, by the way. So, where in Canada?
Oh, Vancouver.
Huh?
Vancouver,
Vancouver.
British Columbia.
So if you've never been to Vancouver, Vancouver is one of the most beautiful cities in the world. Right?
Yes, it is.
You would agree with that?
Oh, definitely.
Uh-huh. At UBC or?
SFU.
I'm sorry?
SFU, Simon Fraser University.
Ah, Simon Fraser University. That's in Vancouver also?
Yes, it is.
I didn't know that. Uh-huh.
Burnaby, technically.
I'm sorry?
Around Vancouver, in Burnaby. So my question was, as we start to move away from Moore's law, as in relying on the
We're not
number...
moving away, we're stuck.
Or stuck, as we can no longer rely on the number of transistors on a chip to quantify our computing power, advances in computing power. Do you have any insights into how if any new law might manifest that describes our advances in computing power as we use a hybrid of the technologies that you described, or will it become somewhat more unpredictable as we advance?
Yeah, so it's going to be much more unpredictable. The Moore's law, by the way, is just an observation that Gordon Moore made. And as I mentioned when I was talking, a lot of psychology, that it seems like, and I've been around since a very long time, and every few years people would say, okay, Moore's law was good, but now it's over. And then something would happen and it would continue. And I really believe it continued because the pressure was, if you don't do it and they do, you're going to be, working at McDonald's or something or other, or KFC or something. But finally, we get so small that it's over, or it will be over in another, I don't know, certainly less than 10 years. And in fact, when it's over, we will have on the chip. In fact, when he introduced me, he mentioned it, 50 billion transistors. So that's far more than we know how to take advantage of yet. It's also far more than we can power up at any one time. So we're going to have this dark silicon problem that I mentioned. Your point is very well taken about predictability, that we do seem to have been on a curve that's fairly predictable, that we call it process generation, every new set of chips was doubling the number of transistors. That has stopped, even though it's still possible, because the energy required to power all those transistors has been too much. And so if you look at the curve, it's kind of tapered off. But the capability is still there, and it will be still there until we get down to so small a size that we just can't build transistors anymore. And that's going to happen probably, this is what now, 2017, I don't know, another 6 or 7 years probably. And we'll have 50 billion transistors. Now the heart of your question was, will there be any law that replaces it? I don't know of any. Will it be unpredictable, you ask? Most of the people that I talk to that are thinking like I am about what do we do next, most of us agree that it will be unpredictable. That is, somebody will come up with an algorithm that's going to make a big leap, and then for years there'll be nothing, and then another big leap. I believe this concept of accelerators with the von Neumann machine as the basic structure that keeps everything orderly is the way to go. As he mentioned about this quantum computer, it won't be a computer, it'll be an accelerator. But right now, he says this company in China, 4 qubits. We're going to need a lot more than that. At some point, it may be the company in China, it may be Microsoft. Somebody's going to figure out how to get enough qubits that's going to solve that problem. What that's going to do is give a big boost to that set of applications that require the quantum accelerator. In fact, I think a big part of the future deals with this concept called domain-specific applications. So you build a machine to do a particular kind of thing. The things you do with your with this thing, very different than what you do with your laptop, for example. So the algorithms that will require your smartphone, as time goes by, will make a jump in understanding, which will solve that set of problems. It's also the case, I think, that the tools available to design these accelerators is going to be important, and improvements in that is going to accelerate our ability to compute. I guess the bottom line is that it's a new world out there with, so Moore's Law, instead of saying, okay, now we're done, it says, okay, we're no longer able to relax. We've got this now limit. There's got to be other things that are going to have to come to play. I think I used a term in one of my slides. We're going to have to design smarter, which is why I advocate knowing all the layers as a way to help you design smarter. But as far as a replacement law goes, I don't see it, and I agree with you, it's unpredictable. And what's going to happen is nothing for whoop, nothing whoop, and who's going to make those advances, I don't know.
Thank you.
Sure.
Hi, Professor. I want to ask a question about the microarchitecture.
About?
Microarchitecture.
Vector?
Microarchitecture.
Vector architecture.
Yeah.
Yeah.
In the conventional system, the microarchitecture serves as a interface between the hardware and the software. Hardware such as device and circuit.
Software. You're starting. So you were good for a while, and then all of a sudden you just sped it up, and you lost me. So you say that a vector architecture.
No, microarchitecture.
Oh, you're not talking about vector, you're talking about microarchitecture.
Yeah.
Okay.
I'm sorry.
Okay,
Yeah.
so a microarchitecture is...
The microarchitecture serves...
between the software and the hardware.
Yeah,
Yes.
it's an interface.
Well, okay, I prefer to think of it as an implementation, but
Yeah.
if you want to think of it as an interface, okay.
Yeah.
Go ahead.
And I'm wondering, what do you think is the position of microarchitecture in the novel computing systems, such as the reconfigurable system and heterogeneous systems?
So, first of all, I guess you could think of any one of these layers as an interface. I choose not to. What I like to think of each one of these layers is a capability of getting from here to here. It's not the interface, it's the stuff that does the job. And the job of the microarchitecture is to recognize that I have circuits available to me, and what I need to do with the microarchitecture layer is use those circuits to build the capability that if a compiler gives me the zeros and ones, I can carry out the program that zeros and ones carry using the circuits that are available. And that's the microarchitecture. Reconfigurable is part of the microarchitecture. It has been for some time. You probably know the term FPGA.
Yeah.
FPGAs are part of the microarchitecture. You will see, or I don't know whether we have them yet or not, but it is certainly the case right now that the CPU designers are planning on, as I say, they may have already done it and I'm not aware of it, but they're certainly planning on having an FPGA be part of what's on the chip. It'll be part of the microarchitecture. And in fact, you see it right there. ASICs, which is hardware, FPGAs, which is hardware that's reconfigurable, and then changing the microcode. If you put on the chip an FPGA and you want to use that FPGA to participate in the computing, what you first have to do is load up all the architecture bits that tailor the FPGA to the particular job that you want to do right now. So what's going to happen is if the compiler says, use this FPGA to do this job, What the compiler will have to do is generate the code that will allow the architecture bits of the FPGA to first be loaded, then you can use it. It's the microarchitecture's job to do the loading and then the using, which means that when I design the chip, I will have an FPGA on that chip, and I will have the interconnection structure to be able to load all the architecture bits of the FPGA. FPGAs, as an example of reconfigurable, is very clearly part of the microarchitecture. Does that answer your question or not?
Yeah.
Okay.
And another question is about the compiler. And I want to know the relationship between the architecture and the compiler, because many students who learn computer architecture finally find a job of compiler. For example, your famous student, Professor Wenmei Hu, in University of Illinois.
My famous student. Why is he my famous student? Because he's Chinese, of course, right?
No, because we all use CUDA now.
I'm sorry?
CUDA.
Yeah, he is certainly. So what he's doing now. So Professor Hu, Wenmei Hu, who's now one of the biggest famous professors at the University of Illinois. That's true, and he's done many things. As you point out, at one point he designed the compiler, the Impact compiler. And now what he's doing is using CUDA. But what's important about what he's doing now is trying to take problems that in the past have never been used, have never been, so how do I say this? Taking problems that in the past nobody ever thought they'd be able to be solved using a GPU, and teaching students how to take that problem and represent it in a way that it can be programmed with CUDA and then executed on a GPU. So that's what he's been doing lately. So what's the question about Professor Hu?
No, I just want to know the relationship between the architecture and compiler.
And the compiler, yeah. So first of all, if I go back to here, you see that bullet ISA, which is the instruction set architecture. I would argue that that's the interface. In fact, I wouldn't argue, I would tell you. It's the interface between the software, and the last step of the software is the compiler producing the zeros and ones of the program. And then the microarchitecture takes those zeros and ones and produces the ability to carry out that program. So the relationship between the compiler, in fact, it's not shown as a level, but rather I think of it as, I don't know whether you can you see that dot or not? It's the level that's taking the program and producing the zeros and ones. So it's crossing that boundary, is the compiler. If I'm going to write a good compiler, I have to understand the ISA. If I'm going to design an ISA, I have to understand the stuff above, including what the compiler is able to do. So Professor Hu, who got his PhD with me back at Berkeley, it's 30 years ago now, 1987. I'm still young, but he's now an old man, see? He did his research with me in microarchitecture. He was one of the students that worked with me on the HPS model, for example. Then when he moved to Illinois after he graduated, he got into compilers. Because he understood the microarchitecture, he was able to write a better compiler. So the relationship between the compiler and the microarchitecture is absolutely critical. It's been critical to his work. It's been critical to a lot of other work we've seen. For example, a number of computers embrace the concept of predicated execution, which gets rid of branch instructions. Why did that happen? Because somebody recognized that if I have the capability to predicate, the compiler can generate these one-bit predicates, and then the microarchitecture can either go this way or that way based on that predicate, and I don't have to have a branch instruction. And so it's sped up processing. That never would have happened if there weren't compiler people and microarchitects that talked together. Because they did, we have predicated execution. So I guess the short answer to your question is that compiler technology and microarchitecture, if you want to do one of them as a career, you better know the other one as well. Because your ability to do one is going to be in a large way based on your understanding of the other.
Thank you, Professor.
We run out of our time, so I want to let the person, there to ask the last question.
The last question. So the last question is the one that some of you have been hoping for, so we can get out of here, huh? Go ahead. No, the end of the Moore's Law will not break down the layers. What the end of Moore's Law will do is tell us that we better do something else because we no longer have Moore's Law. And my suggestion is that what we will do to compensate that we don't anymore have benefit from Moore's Law is we will break down the layers. Whoa. So I missed an important sentence. I was following you all the way up to, you say you think the layers are important because, and then your voice got soft and I didn't understand what you said. So I'm not understanding what you're telling me. It allows what?
For example, when you have to go, okay, website, you don't want to understand, you don't want to care about the hardware details under your program. So those layers can help us to develop our software more efficiently. And so I think that from my perspective, I think that the problem is that now we have a lot of cores, but we did not use most of them. So can we just add one more layer in this hierarchy to parallelize those programs so that all the programmers can stay in their current state and focus on their own business and don't care about other things? So is that possible?
So that's been tried for a very long time. And it hasn't worked yet. There was, you said something that I wanted to comment on, and, so I know. So there are several things to say. The first thing to say is the thrust of my talk today is what do we do to compensate for we will no longer have Moore's Law? So what has Moore's Law given us? It's given us a lot more transistors so that we can invent structures that make computing go faster. And it's given us a much smaller transistor, which means we can process at a much higher frequency, which means we can make things go faster. So what Moore's Law has given us is the ability to do more stuff, more exciting stuff. If you were at the ceremony last night, or if you watched the video of that ceremony, you will see a lot of things going on very, very fast. if the computer that was doing what was done last night at that celebration was the computer of 25 years ago, you would have been bored. You would have sat there and said, oh, this is not very interesting. There are two kinds of things that we deal with in computing. Do we want to design the application in such a way that it goes very, very fast? Or do we want to get it done very, very quickly? These are get it done, meaning write the algorithm very, very quickly. So if a company hires you to write a program that's going to cure cancer, you're going to want that program to run very, very fast, because if it doesn't run fast, the patient will be dead before the program finishes. It's not acceptable. So knowing the hardware to the point that you can get that program to run much faster is what's important. If the company hires you to write a program that will take the number of hours each employee worked, multiply it by the hourly salary that the person gets, and print the paycheck that the person deserves so you can send it to the bank so the person can then spend the money, that program, you don't care how fast it executes. You want to write the program very fast so you can get on with other things. There is no question that you can write a program for the web that you can get done much faster, but if it doesn't do the computing much faster, you're probably going to have a problem selling that web application to somebody who cares about how long it takes. So, for example, there is a company in the U.S., you also have a company in China, so maybe you've never heard of the company in the U.S. It's called Google. The engineers that program these computers to do the searching, etc., in Google are very comfortable and knowledgeable about the underlying layers, because they count on the underlying layers to make those searches go as fast as possible. You're absolutely correct that if you were to make the layer and say, I don't care what goes on underneath, I care about getting my problem solved, writing my program as fast as possible, you're absolutely correct. You can write the program faster if you have an interface that you don't care about what goes on below that interface. The issue is, do you care about how fast that program you write will execute? If you don't, I absolutely agree with you. Have a layer, don't worry about anything below. But if you do care, then knowing what goes on at the lower levels will make a big difference in that application you write. By the way, let me add one more point before you do. Knowing about that, so it's important that you graduate before you retire. That is, we don't want you to graduate and then immediately retire. We expect that after you graduate, you'll have a lot of years to work. So we can't take that 4 years of college and make it 44 years of college. So it's not going to be the case that you can be an expert in each one of these layers. But you have to know enough about the other layers to enable you to do your layer job better, and also to be able to communicate, to talk to those people who are working at those other layers. Okay. Yeah, so I have a lecture where I call it mega nonsense. So you have many cores and mega nonsense. And one of my bullets in that talk, or one of my pieces of nonsense, is people say thinking in parallel is hard. And so I display on the screen, thinking in parallel is hard. And then what I do is I hit the button, and in parallel is removed from the sentence. And what it says is, thinking is hard. Right? I have a very good friend who's a very senior professor at the University of Wisconsin. His name is Guri Sohi, Indian. And he agrees with you 100%. He says that what we need to do is have that layer which allows people to think sequentially, and that layer will turn their sequential result into the parallel program, which is what you're advocating. And he believes very strongly that that is absolutely the way to go. What I would like to do is actually have two interfaces to the computer. One interface for the person who's not able to think in parallel, and that person can write the straightforward code. The other interface is for the person who can think in parallel. That person can write better code. But what's missing is what you suggest, is the layer that takes the code written by the not terrific programmer, and by the way, for every terrific programmer, there are plenty of non-terrific programmers. But that layer that you suggest, which Professor Sohi suggests, to take that sequential code and turn it into what the expert programmer could have produced, because the expert programmer understands the underlying hardware. And maybe someday we'll be there. It's certainly an objective that we should look toward. My pleasure.